Hello everyone, welcome to my YouTube channel School of Chemistry. So in continuation with the topic of hybridization, today we are going to study hybridization of elements involving d orbital. So as we know that d orbital is present in the element of the third period. So from the third period we have 3s, 3p and 3d orbital. 3s, 3p and 3d orbital, and their energies are comparable. Energies are energies are comparable. So the 3s, 3p and 3d orbital can be involved in the hybridization, and we can also see that the energy of 3d is also comparable to 4s and 4p orbital. So these can also be involved as their energies are also comparable. But there is a huge difference in the energy of, we can say, 3p and 4s orbital. So that's why we cannot have 3p, we cannot have 3p, 3d and 4s orbitals together, because due to huge difference, huge energy difference between 3p and 4s orbitals. So the first example today I am taking with the d orbital involved in the hybridization is formation of PCl5. If we talk about the central atom, that is phosphorus, so we can write down the electronic configuration of phosphorus as 1s2, 2s2, 2p6, 3s2 and 3p3. It has 2 electrons in the 3s orbital and 3 electrons in the 3p orbital. So we can represent it like this: 2 electrons are there in, and 3 electrons are present in 1, 2, 3, and we have an empty d orbital. This one is our 3d orbital, this is 3p, this one is 3s. So what happens is the electronic configuration in the ground state. So in the excited state, one of the electron from the 3s gets excited to the 3d orbital, and in the excited state the electronic configuration will look like this. One electron is present in 3s orbital, 3 electrons are present in the 3p orbital, 1, 2, 3, and 1 electron is present in 3d orbital. These electrons, one of the 3s, 3 of the 3p and 1 of the 3d, undergo the process of hybridization, that is sp3d. So as in total 5 orbitals are involved in the hybridization, so we will be getting 5 new hybrid orbitals. And they will align themselves in 3 dimension in such a way that they will have minimum repulsion and maximum stability. So in order to that, they will acquire a trigonal bipyramidal geometry, which appears to be like this. So one of the chlorine atom is present over here, with its p orbital is going to overlap with the hybrid orbital. One will be lying over here. One at the bottom. and this is at the equatorial plane. This one also at the equatorial plane. So three of the chlorine atoms are present at the equatorial position. These three, they are present at equatorial position, and two are present at axial. That is, one above the plane, one below the plane. So the bond angle, two type of bond angles are there. This is of 120 degree and this bond angle is of 90 degrees. So the axial bonds in PCl5 are longer as compared to the equatorial bond. That is due to the repulsion caused by the electron present in the equatorial plane having an angle of 120 degree. So they are going to repel this electron, or the atoms presented axially present a one above the plane, one below the plane, which are lying perpendicular to the three atoms. So the axial bonds are longer as compared to the equatorial bond. That is due to the more repulsion caused by the atoms present at equatorial plane. Next example involving the d orbital is of, second example is formation of SF6, and this will be involving the hybridization sp3d2. So if we look at the outer electronic configuration of sulfur, I am only writing the outermost electronic configuration, that it would be 3s2, 3p4 and 3d0, and which could be represented as 2 electrons in the 3s orbital, 4 electrons are present in the 3p, 1 2 3 4, and we don't have any electron in the 3d, but representing like this as an empty orbital. So what happens, one of the electron from the 3s move to the 3d orbital and one electron from 3s, one from 3p, one from 3s. So this was the electronic configuration in the ground state, and in the excited state we can represent it as one electron in the 3s orbital, 3 electrons in the 3p orbital, 1 2 3, and 2 electrons in the 3d orbital, 1 2. So a total we have sp3d2 sp3d2 hybridization involving 6 orbital in the hybridization. So we'll be getting 6 new hybrid orbitals, and they will be 6 new hybrid orbitals will be formed, and they will align themselves in 3 dimension in such a way that they will have minimum repulsion and maximum stability. So they acquires the shape of an octahedral. So one above the plane, one below the plane, and 4 of the orbitals will be present in the plane. Something like this. So if I represent fluorine over here, so that's going to overlap with its p orbital. Fluorine over here overlapping with its p orbital. Again fluorine over here overlapping with its p orbital. Let me draw it like this. Okay, one fluorine over, it should be fluorine, one fluorine over here. Okay, then we have a fluorine atom over here, fluorine atom over here. So it appears to be something like this. So all the angles in this will be of 90 degree, and this will be an octahedral geometry. So these are the hybridization involving the d orbital. We can have certain more examples in which d sp2 hybridization would be there, sp3 d2 hybridization is there, and we can have d2 sp3 instead of sp3 d2. When the inner d orbital is used, that we can have d2 sp3. Those of type of hybridization we will study in the coordination compounds. Hope these videos are helping you in your studies, and for more interesting videos please like and subscribe to my YouTube channel School of Chemistry. Thank you.